Welcome back, Physics 20s, to your next lesson in Chapter 5. This is 5.3, and we're looking at vertical circular motion. I'm going to start with a scenario where, let's say we take a bucket of water, and someone claims that they could take it and lift it upside down like this, and that no water is going to fall out. Well, you'd think we know how gravity works. It pulls everything to the ground. There's no way that could happen. But yet the person takes the bucket, and they swing it around like this, and holy crap, it doesn't even fall out. No water comes out the whole time they spin it. And in your amazement, they claim it's magic. They're this magic person that was able to keep the water in the bucket. But we're going to explain today how that's going to work, and it's not magic, it's physics. And we're going to explain how that works with vertical circular motion. So let's start with looking at the bucket on its own, and we're not even going to look at it spinning so far. We're just going to look at it if it was hanging. So at the bottom of the circle, we have some forces acting on it. If I'm going to draw a free body diagram here, there's a force acting downwards on the bucket, and that's the force of gravity. But also in this position, because of the string, there's a force going up on the bucket as well, and that would be the force of tension. So if you're just holding a bucket at the bottom, there's going to be Fg and Ft acting on it, right? But if we consider at the top, well, there's still gravity acting on this, so we're still going to have a force down of Fg. And if this wasn't spinning around in a circle, gravity would be the only thing pulling this. There wouldn't be any tension in the string because that'd be going down as well, so the bucket would just fall. All right, but now let's consider what happens in circular motion. All right, so we're going to look at the bucket at the bottom, and let's say it's spinning in a circle that looks like that. We have our Fg, which I'm going to put in red this time. We have our Fg pulling down, and I'm going to draw my forces a little bit different this time. I'm going to draw them in adding up, kind of like we did with vectors in chapter 1 and 2 to what the net force was going to be. Now, what we had in the first scenario was we had our tension going in the upwards direction like this, and they were the same length. Fg and Ft would cancel out, so their net force was 0, and it would just be sitting there. But now we're going to change it that when it's spinning in a circle, there needs to be a net force that is Fc, right? It needs to be accelerating in a circle, which is Fc. So I'm going to draw that next, right here in green, going upwards, right? And this is our Fc. Now that's what we need the overall force to be, providing a centripetal force. So now I'm going to have to change the tension by making it significantly bigger, all right? This is our new Ft, because the tension now has to overcome the force of gravity, like we did initially, and provide a centripetal force. So that's going to make it so there's more tension at the bottom of the circle. Now let's take a look at the top of the circle. So I have it at the top, and it's traveling in a circle like that. And again, I'm going to start with the force of gravity like we had from before, and showing that in red from the center of the bucket. Here's our Fg. Now, there was no tension in this before because it's just falling down due to gravity. Gravity would be pulling it down, and the tension would be pulling it down. So there's no tension. It would just be falling. But now we're going to add that Fc in green here. So I'm going to draw it again just to the side. And our net force has to be going down anyway to make this go in a circle. We need a force pulling it towards the center, so our Fg can provide that. And so if it's going around in a circle, the Fg is providing that centripetal force, and it's able to go around in a circle. Now I've drawn them as completely equal here, and this would be if you're matching the exact speed needed to go around in a circle of that radius. But what if we start to spin it faster? Well, mv squared over r is equal to our Fc. So if I'm increasing it, making it go faster, increasing my velocity, the Fc required is going to go up. So I'm going to draw that arrow as quite a bit bigger. So what would happen in this case if we have Fg pulling down, but it's not enough to make it go in this circle with our large required Fc? Well, we need another force to keep pulling it downwards in that direction, and that's going to be the force of tension. So I'm going to draw that in here, Ft, all right? So that's if you start spinning faster than the minimum amount required to make up for the Fc that isn't being provided by Fg, we have force of tension. So Fc is the force we need towards the center of the circle. It's provided by Fg and Ft. All right, let's put this together in one diagram, and I'll show you how I would draw this for doing a question. I would actually start by drawing the centripetal force from going from the center of the bucket towards the middle. Now we need it during the whole circle, so I'm going to draw it for both of them. I'll put it in green here, from the center of the mass all the way to the center, of the circle, from center of mass to the center of circle. I'm going to label those FC. That's what we need to end up with. At the top and at the bottom, we need that FC to be provided for it to go in a circle. Next, I'm going to put FG because we can't get rid of that, and it's always going to be acting downwards. So I'm going to draw it going down here on the bucket at the bottom, and going down here at the bucket on the bucket at the top. All right, we know gravity always acts down. It's pulling in that direction. Now, this is going to leave room for our last one, which is tension, which is going to be different in each case. So I'm going to use orange, and let's start with the bottom of the circle. The tension has to overcome just fighting against gravity, and then has to provide that centripetal force as well. So the Ft is going to be our biggest force at the bottom of the circle. However, at the top, Fc needs to be provided by Fg, and it still needs a little bit more help. So to make enough centripetal force towards the center of the circle, we just need a little bit of tension at the top. So hopefully you can see that the Fc's are the same, always towards the center of the circle. The Fg's are the same, always towards the ground or downwards, but the tension changes significantly from the top to the bottom. So I'm going to write an equation that we're going to use for calculating tension at the top and the bottom of the circle over here at the side in blue. So let's first look at the bottom of the circle. Okay, I think it's easiest in this case to not really consider plus and minus, because that's going to be kind of difficult to keep track of. So I'm actually going to come up with a way to solve these with using all of these values as positive. Okay, so how I'm going to do that is looking at the bottom here, I'm going to say, well, what's the biggest force? The biggest force is the force of tension. So I'm going to say Ft is equal to Fc plus Fg. Because if I look at the lengths here, this Fg plus this Fc has to add up to the force of tension. So that's what I'm going to use. I get to keep all those values as positive. Ft is equal to Fc plus Fg. All right, and that's all positive values, which I think makes it easier, then we don't have to keep track of signs. Now if I look at the top part of the circle, I can kind of do the same process, but I see in this case Fc is the biggest one, and it's made out of Fg and Ft. So now I'm going to write Fc is equal to Fg plus Ft. All right, that's the formula that I like to use for the top of the circle. Okay, this isn't on your formula sheet. These ones here, they do have some formulas on there that do take into account plus and minus, and I think it's a little bit harder to use. So this is the way that I like to solve them, and I think is going to be easiest for you to do that. So let's give you some examples for how to solve these questions. So our first example, a 2.0 kilogram mass is swung in a vertical circle of radius 0.80 meters on a string. What is the tension in the string when the mass is at the top and at the bottom of the circle? Okay, so here's our mass. It's 2.0 kilograms, and it's swinging in a circle. Let's start with calculating at the bottom. Okay, so just to recap those forces from before, we said, well, we need an Fc going up, Fg is pulling down, so tension needs to overcome gravity and provide that centripetal force, Ft, like that. So I get really used to drawing those diagrams. You could draw those on a test at any time. And just from the diagram, we can see that Ft is the biggest one, and it's equal to Fc plus Fg. Right? So to calculate the tension, this is already rearranged for it. I just need to take Fc plus Fg. The formula for Fc is mv squared over r, and Fg is mg. So we just need to add those two up. Let's put in our mass of 2.0 kilograms times the velocity. It actually didn't say the velocity in this one. I should have given you that. Let's say it's going at 3.0 meters per second. All right, that will be in the questions for you to solve them. So let's say 3.0 meters per second. That number gets squared, and we divide by radius of 0.80 meters. Then I'm going to add mg. mg is 2.0 kilograms times gravity, which is 9.81. And And let's see what we get for those. So I'm getting a number for mv squared here to be 22, or sorry, for mv squared over r to be 22.5, and the number for fg to be 19.62. All right, so we just add those together, and I'm getting a number for that to be 42.12 newtons, and I think with 2 digits we would round this to 42 newtons. All right, that's looking at the tension at the bottom, so adding FC and FG. Now let's look at the top. We'll put this in green. Okay, so the force is there. We still need an FC. All right, that needs to be our overall force. Gravity is helping out with that, Fg. And the last little bit to help in maintaining or in achieving our FC is the force of tension there. So in this case, the biggest one is Fc, and that's equal to a sum of Fg plus Ft. All right, so as long as we can draw those diagrams, we can make the formulas from that. Now, this is kind of nice because I've already solved for these values here, so it's just changing how I'm adding and subtracting them. We know that Fc was 22.5, all right, equal to Fg, which was 19.62, plus now we just have to figure out what the tension is here. So I minus my 19.62 minus 19.62, and I'm getting a number there of 2.88 newtons as the force of tension at the top, so much less at the top, and that would round to 2.9 newtons. Okay, so it really helps to be able to draw those diagrams, and then you can come up with these formulas, and it's not too hard from there. Let's do one more. It's going to look at a skateboarding scenario where we have, say someone's trying to do this vertical loop. The skateboarder wants to ride the vertical loop below, which is 6.0 meters high. What's the minimum speed needed to complete that loop? Okay, you definitely want to know how fast you want to go if you were trying that loop. So let's try and figure that out. Well, first let's say where we need to focus on. At the bottom of the loop, the person's going to be fine there. All right, FG is pulling them down. They're going to stay on the ramp. The place we're worried about is at the top. We want to make sure that there's enough speed so this person's actually going to make the loop at the top. So we're going to focus on the top of the circle. So again, what's going on up there is we need a centripetal force going downwards. Let's make that a bit easier to see. Let's maybe use black here. It's a little bit easier to see. We need FC overall. And so how that's going to be provided is with FG. And if that wasn't enough, there would have to be that little bit more. Now, in the last case, this was tension. But in this case, since there's no string, if this person was going so fast that FG wasn't providing enough, this would be Fn. Now, it doesn't change any of the calculations that you do. You just call this Fn instead of Ft. And that's the force being provided by the surface there. And so force is provided by a surface we called Fn. So that would be if they're going plenty fast. But we're actually not talking about, they're going really fast and they have a normal force. We're talking about the minimum speed that you need to acquire this. So let's say you were going really fast and there was a normal force, and you start slowing down, you start reducing your FC, and you start reducing the normal force. So keep reducing these until you get right to here where the FC is equal to the FG, all right? And we're not going any extra speed, no pressure against the top of the loop, just FC is equal to FG, all right? So that's where we're gonna start with our formula, as FC is equal to FG. Now again, if he's going faster, there would be a plus a normal force. We're saying go so slow that there's no normal force, the minimum speed. So now we put in our formula of mv squared over r is equal to mg. And now that we don't have that normal force in there, we notice that we have a mass and a mass on both sides, and they can cancel out, which is good because it didn't tell us the mass in the question. All right, so now to rearrange, we just times by r on that side and square root to get v is equal to the square root of gr, or kind of like GR, like we saw from the previous lessons. So let's just plug in our numbers there. V is equal to 9.81 meters per second squared times our radius. Now, I think it's quick to just put in 6 meters. We have to think if this is 6 meters high from here to here, we're only looking for the radius, so that's only half of the way up. So we're actually going to put 3.0 meters in there because it's just the radius, and square root, and I'm getting a number of 5.4 meters per second is how fast you'll have to go to make that vertical loop. Okay, so now I've seen an example with looking at tension at the top and bottom and looking about a minimum speed question. That should hopefully give you a good idea on how to do those practice questions. Give them a try, and I will see you in the next video.